So in this audience, Swagato actually does not need an introduction, but just for those who may not know him, Swagato did his PhD in TIFR a long time back. He was in the same batch as one of our colleagues, Rajdeep. And during his PhD days, he was expert on all the dives in Kulaba. After leaving, he did a couple of postdocs and then became a staff member at Brookhaven, where he remains. He is one of the leading lights of the RBRC or Hot QCD collaboration, as it is now called. And he'll be talking about some of his work with them. So thank you, Swagato.
Thank you, Shorendu. Thank you, everyone else. Would have been a pleasure to be there and give the talk there, but it's also a challenging job, and particularly the topic what Shorendu gave, which I thought is a pretty technical one, and it's difficult to do justice or for a colloquium, and with many others, which like students who are non-high energy or non-expert. So I will try, and bear with me at least for the first 5 minutes, because I didn't know the audience at all. So I wanted to give a start from very basics, and so and see how much I can do, and to keep it at a level which probably understandable to everyone. And it's a tough job giving a talk in DTP. I'm still feeling the butterflies in my stomach after so many years and with so much gray hairs. So let me just start. So as you all know, at least, there are atoms. Atoms are made out of electrons and protons. Protons are made out of quarks, which are bound together by some bosons, some gauge bosons called gluons. And they are bound together by a force, which is known as the strong force of nature. And the fundamental theory that governs this strong force is known as quantum thermodynamics. The quarks and gluons comes in three varieties. They're called colors. But we cannot see these individual varieties in nature as we see it. It comes as a bound states of all the things combined together, such that it is a colorless object. But as energy or temperature increases, and the interaction strength of the strong force gets smaller, weaker and weaker, and eventually in a very high energy, infinite energy limit, the matter becomes free. This is known as the asymptotic freedom. So if you heat up matter at a very high temperature, like 1 billion degrees Celsius, then quarks and gluons no longer remain confined within the protons or the nucleons. And what comes out, or what you find, is a colored soup of quarks and gluons. This is known as the core-gluon plasma. Such an object or such a matter existed like a microsecond after Big Bang. And obviously it doesn't exist now, but it used to exist at least we think so, in the microsecond of the Big Bang, such a soup. But obviously we cannot see that, but what we can do now is we can create or recreate this core-gluon plasma in colliding heavy ions, which are moving in the speed of light, and then or close to the speed of light, and with banks and collide themselves. In such a collisions, high energy collisions, we expect that core-gluon plasma is created. And obviously what we see after that is when it rehadronizes and forms that. Forms back to hadrons, and that's what comes to the detector, and that's what we see. By looking at this final reformed hadrons, we try to infer what was created and whether core-gluon plasma was formed. So this kinds of atom smashes exist. Obviously, one famous example is the Large Hadron Collider at CERN. Particularly, this ALICE experiment here is dedicated to this to study the properties of such a matter. There's also another accelerator which is still going on, which is my home right now, which is the Brookhaven lab with the relativistic heavy ion collider. The relativistic heavy ion collider is a little bit more flexible. It can vary the energies of these collisions. You can change the energies of the collision and control how fast these nucleons are moving towards each other. And by doing that, what you can do is you can lower the energies, and so that a bunch of nucleons and more nucleons get stopped. And what you can form is basically what you can do is you can paper this quark-gluon soup with by adding more quarks than antiquarks, or adding baryon density to it. So then what that gives us is basically a tool. By varying this energy, it gives us a tool to explore a phase diagram of QCD as a function of temperature and baryon density, or the baryon chemical potential. The question that we really ask, or will be asking in this case, is how to get the properties of this quark-gluon plasma, particularly as a function of baryon density or baryon chemical potential, starting from the fundamental theory of QCD. And the problem there is at the scale where all these things happen, the transition to hadrons to quark-gluon plasma happen, the coupling is very large, of the order of 1. So normally all these tools of PQCD like expansion completely fails. So what we really need is a non-perturbative technique to address this question from theory. And the technique that we are going to talk about today is the lattice QCD. So what you do is here, you just take the QCD Lagrangians straightforwardly and regularize that Lagrangian, that field theory on a lattice, and where all the quarks lives on the sides of the lattice, and the links between these two sides that connects are the gluons. You put the gluons between the links of these two sides such that all the quarks, the gluons interacts, and you put this in QCD in its full glory, just only that you put it in a 4-dimensional box with 3-dimensional space and 1 Euclidean time or imaginary time. But such a thing is has tons of degrees. A very modest lattice of 64 to the 4th will have like a billion variable, and you have to do or evaluate this path integral of billion variables. So obviously you need a supercomputer to do this. So that's what we do, and that's the techniques that we are going to use. Now, what we actually do is in this technique is we take the partition function, which is sort of has two parts in the action, like the gauge fields, which are the pure gauge, like the actions of the gluons, and the actions of the fermions. Now, for any observables that we want to write, some observable O will be just integral over this partition function and some observable. So normally, how do we perform this integral or this path integral? So what we do is, obviously we cannot do exact integral over billions of variables. So what we evaluate, the way we evaluate this integral is the standard Monte Carlo technique. So what we do is we measure this object O on each gauge field background, and we generate many gauge fields background, which are distributed according to the probability of this action. Yeah. So by doing this sampling and by summing over all the measurements over this many ensembles of these gauge fields, what we get, we can measure, or sort of we can estimate any observable. And that's starting from first principle QCD without essentially a parameter-free way of doing it. So what's the problem? The problem is, what we wanted to do, as I said, that we want to do this calculations at finite baryon density, or at which means at finite non-zero value of chemical potential. So the problem that becomes at the non-zero value of the chemical potential is this fermion action, or this determinant of the fermion matrix, becomes complex. So once it becomes complex, obviously you cannot treat this as a probability and distribute your gauge fields according to this, because it's a complex number. So standard way of doing these things at Monte Carlo sampling completely fails. It is not a problem when the mu b equals 0, then this determinant is positive definite, and so on. All properties of probability, you can do it perfectly fine. But once you add a non-zero chemical potential, this completely fails. You cannot just sample the gauge fields which are distributed according to this probabilistic interpretation of the action. So what do you do? So what is done are usually there are many other techniques, but one of the most successful techniques, which was also pioneered by Rajiv and Sarandu, is called the Taylor's expansion. So what we do in the Taylor's expansion method is basically, let's start with an observable, like a thermodynamic or equation of state, the pressure. So what you do is you expand the pressure in power series of mu at a given temperature. So you fix a temperature, set up the temperature, and expand the pressure in just a Taylor expanded around mu equals 0. So at mu equals 0, we can do all calculations perfectly fine. And what we compute at mu equals 0 is the coefficients of this Taylor's expansion. These are known as the baryon number and the generalized susceptibilities. So which are defined as just a straightforward derivative of the logarithm of partition function, but all evaluated at mu b equals 0. So that part we can do. So this expansion, people have done many. Here is one example. There are many of them. Just simply one which where I am involved, or I was involved a long time ago. So it's just the pressure as a function of temperature for different values of mu b by t. And what it also shows is how this, at a given value of mu b by t, how reliable is this expansion. So as you can go from this red band, which is the second order expansion, to up to mu squared, and then mu b to the fourth, to mu b to the sixth, and how it changes, and how this expansion converges or gives you the reliability of this expansion for given mu as a function of temperature. As you see, if when the mu b by t is like roughly 2.5, you see there are strange things, so some non-monotonic behavior develops between as you go from the fourth to the second order, fourth to the sixth order here, close to the transition temperature of 155 MeV at mu b equals 0. So this is sort of how you do normally, how in practice what we do. So we do as much order of calculations that we can, and which is also very limited. The present state of the art is only 8th order. 8th order means you have only 4 coefficients. All the odd coefficients vanishes due to CP symmetry. So it's basically you have 4 coefficients, 2, 4, 6, and 8. That's kind of state of the art. And the only thing that we can do is to what extent it is reliable. We just observe empirically as we go from one order to another order and see whether there is some pathological non-monotonic behavior or not. So that's the best we could do for Taylor's expansion, at least for now. At least we used to do. So a similar thing, it is more pronounced, such this pathological behavior in, for example, in the number density, just the one derivative of the pressure with respect to the chemical potential. And again, you really clearly see that your number density is becoming just simply weird, and definitely it just tells you that it makes no sense to go up to this value of mu, whereas if you have a very small mu of mu or sort of mu b by t of the order of 1, then it's probably okay, you can trust it. But as you go up and up, like mu b by 2, it's already starting to show up, and mu b by 2.5, it's kind of disaster. So there is a very recently, in like this year, beginning of this year, there was a paper, which was published in PRL later today. The people that proposed a new variant of this expansion, and they call it an alternative expansion. But the basic idea is simple and it's straightforward. So what it does in this case is, instead of what we were doing here, take one given temperature and expand this pressure as only in mu. But what they propose to do is, you want to get a pressure at a temperature T and UB. Let's try to get it from a different temperature, T naught, and obviously you have to work with that UB equals 0. So it's just expanding at around a different temperature, which amounts to basically a joint expansion in T and U. So at a different T naught. And then what you can do is you can choose this T naught, the expansion point. You can also make it as a function of u by choosing some physics motivated path in the TMB plane. There was one particular path was chosen in this calculations. Let's not get into the details of it. It pretty much doesn't matter at this point. It's just, what it matters is the basic idea is it's a joint expansion in T and mu for the purpose of this talk. So what it shows here is again the number density, and now you can see that you can go up to 2.5 between different. These are different orders, which you probably shows also in here, and it's sort of, you can still get to 3.5 mu b by t of 3.5. So it kind of improves. Of course, the error gets large. You don't see this obvious non-monotonicities, but it sort of also like pushing the limit. And the errors get large, but empirically there seems to improve the results. But it's again basically based on an expansion of the order of, in this particular case, of mu b to the 4th expansion. But essentially it's also an expansion in u, and in this case a joint in t. So let's basically step back and ask the question: what limits the Taylor's expansion? Obviously, the answer is obvious, that the non-analyticity, so what you're expanding is the log of the partition function. Obviously, the non-analyticity of the partition function in complex mu b plane will limit your expansion. So the obvious example of such non-analyticity is, is that the periodicity of the Fermi-Dirac distribution. So we are talking about the fermions and the fermion determinants, the fermion action. So they will have Fermi-Dirac distributions. Now, in this Fermi-Dirac distributions, if you just send I to mu I mean, just complexify the mu, so mu to mu I, obviously you will straightforwardly immediately see that there's a periodicity at pi. That's which you cannot avoid. So that's one obvious, very periodicity and non-analyticity of the partition function. So it's hard to go beyond that if you are just doing a simple Taylor's expansion. And remember here, this is what we are talking about is 3.5. So it is sort of probably pushing that limit of pi or close enough. So what else? There is a not so obvious one. Now I have to explain this and spend some time on this to explain this. So the not so obvious one that sort of people have understood is called the so-called Young-Lee Age singularity that comes from the chiral transition of QCD. So what is that? So here's a sketch diagram of the QCD phase diagram along for T and mu. This is the phase diagram that we are interested in. On top of it, what we have added is another line, another axis, which is just the quark mass, the light quark mass, the up and down quark masses. So in QCD, in reality, the quark masses are small, but they are non-zero. So we are sitting somewhere here. This is sort of our physical quark mass, let's say. In the limit, when this up-down quark mass goes to 0, so this is this plane here, then what we know is the transition from the symmetric or the hadronic to the quark-gluon plasma phase goes through an exact, like second order phase transition, which belongs to the 3D04 universality class. And this transition is related from the chiral transition of one in the low temperature side. It's chirally symmetric. So every hadron has a chiral partner. It does not have a degenerate chiral partner. It is chirally broken phase in the low temperature phase. And in the QGP phase, it is chirally symmetric. So, so this transition is a second order O4 line. There are hints and something from also Lattice QCD calculation that tells that this transition is second order line of 3D04 universality class. Now, as you come out of the mu and go to the physical value, then obviously there is no exact chiral symmetry of the action. So instead, the second order line turns into a crossover. Now, as you go to larger and larger values of mu, it is expected, or we believe, or we hope that there is that at some point this transition from the electronic to the quark gluon plasma phase actually turns a first order. That happens also at the zero mass limit. So, and when this first order line meets this crossover, or this first order line meets the exact second order transition, the first order line ends at a critical point. This is also a second order transition, but in a different universality class of Ising, 3D Ising. Okay, so we're not going to go to that, but the bottom line, once you have a chiral transition, and since the physical quark masses are small, so they then probably they're likely, we don't know, there are some hints from Lattice QCD calculation that the order parameter, for example, will satisfy some scaling. The order parameter is just a derivative of the partition function, which also means the partition function satisfies some scaling, which is some universal scaling, which is governed by the universality class. Either it is Z2 here, or it's O4 here, or something like that. Now, this universal scaling of the order parameter is some quark mass to the some power, and then it comes with a universal scaling function. This is all known, very well known. Now, this universal scaling function is a function of everything that does not break your chiral symmetry explicitly, because we are only talking about chiral symmetry. So what breaks your chiral symmetry explicitly is the quark mass, and everything that does not break your chiral symmetry goes into the scaling function, and which will be the temperature, and also, if you are here, the chemical potential. Now, CP symmetry demands that it has to come in the even powers of mu, so to the leading order, we just write it as mu squared. And there are other things that, here will be there. I mean, obviously, the scaling variable that connect to that maps the temperature and chemical potential to the scaling variable will determine of some non-universal parameters, such as the Z naught, TC naught, and this kappa. There are some non-universal constant, which is unique for QCD, but it is not a universal thing among various different systems. But you can estimate or evaluate this from Lattice QCD, because it's unique to QCD. But this scaling function, which is a function of temperature as well as the chemical potential, the scaling function of G, it is universal from different systems for different systems. But we also know that because of this universality, that this scaling function is non-analytic in the complex Z plane. So the non-analyticity in this complex Z plane goes as something like Z minus ZC to the some fractional power or tiny power of 0.1. And the ZC is also governed by the critical exponents, some critical exponents. And the value that it is also universal. Because this function is universal, its singularities are also universal. And it is known. I mean, it wasn't known, the singularity, the value of the singularity was actually calculated only a year ago. It was surprising that it wasn't known. So this singularity of the scaling function is known as the Young Age singularity. Now, since there is a, so this is the Youngly Age singularity is a singularity of the partition function, and the scaling variable is a function of mu. So that also means that you also have an inherent non-analyticity in mu, in the chemical potential, that comes from the underlying chiral symmetry or chiral transition, or the universality class of the chiral transition of the QCD. So how does it look like? So roughly what it looks like, so once where you have a second order transition, this is a second exact phase transition, the singularity must lie in the real chemical potential. For example, when I'm in the chiral limit and I'm sitting here at this transition, this at any on the transition line, say for example at here at this T1, I have a second order transition. So the singularity at this mu1 here must lie in the real axis. That's the definition of second order transition. Now, when I'm sitting here for realistic QCD, obviously there is no second order phase transition, it's a crossover. So what it means, this singularity in view, this non-analyticity in view, it moves to the complex mu plane. And again, when I come to this critical endpoint, I have another second order transition. At some point, the singularity will start moving along this line and pinch the real axis. That's where I will have another second order transition, which is the critical endpoint. So this is basically, it is the Youngly Age singularity, which comes from in the scaling variable plane. It is a cut, and the age, just DC, is just the age of this Youngly, and this cut, which is known as the Youngly Age singularity. So this singularity inherently puts some non-analytic behavior in mu in the QCD partition function. So, which means I can also try to estimate that, since I know the universal value of the singularity, that's a universal thing. And all these non-universal quantities, there are a few things here, can be estimated from actual lattice QCD calculations. By doing that, but using this universal number and this non-universal but QCD calculated numbers, I can estimate what the radius of convergence of the Taylor series can be from this Liang age. And well, as it turns out, is a function of T and UB. This is the radius of convergence in UB, and that would be different for different values of T, because this mapping depends on T itself. So for different values of T, this will be different, this radius of convergence, and this line shows what the radius of convergence is as a function of T, and also for different values of the quark mass. If the quark mass is 0 in the chiral limit, obviously you have a singularity right at mu equals 0, because there is a second order transition. So the radius of convergence has to be 0. It's an essential singularity. As the quark mass increases, the radius of convergence increases. So this is some estimate of some realistic estimate, but the next estimate for ideal cases, assuming everything is in the continuum and so on, everything follows the universality. So this is something when as you increase the quark mass, so you see the radius of convergence increases, and roughly at the physical mass, you expect somewhere here. That's I would say that's sort of the upper bound that we can estimate from the numbers. So what? So can we see the question that we can predict? Now we know what can limit this radius of convergence of the Taylor series. The question is, can we capture them? Can we get it? And to better, can we go past them? So where is this Youngly Age singularity, and what lies beyond this? So what we actually need to do this is obvious. So you cannot do it by a Taylor's expansion. It is very difficult. So we need some kind of resummation of this Taylor series. So one particular resummation, which has been very successful in all across various fields of physics, is the Pave resummation of a Taylor expansion. So what you basically do in that case is you just reexpress your Taylor power series in some values, in a series where you have basically a series of poles. That's the essence of Pauli approximation. Of course, you need sophisticated things to do this, but this is sort of what you are trying to look is basically trying to look for the singularities of the series by re-expressing them as a sum of poles. And this was done by Rajiv Sorendu and also Somen, and was actually introduced to this field by Rajiv and Sorendu. And this shows one of their results. So this is the pressure as a function of baryon chemical potential for various values of temperature in units of the transition temperature will be equal to 0. So and these are the Pade-Resum results of the Taylor's expansion. As you see around 1.5, maybe by T of 1.5 or so, it seems that breaks down. Is this the question is this the hint of Yang-Lee Age singularities, and how can we go beyond? The difficulty, at least from what I understand in doing this, is you still rely on the Taylor's expansion, and you only have them as much as you have them, and the higher orders are very noisy. So this method is, of course, also ultimately is limited by the available orders of the Taylor's expansion as well as the efficacy. So if you have up to 8th order or only 4 coefficients here, you cannot get anything which is more than utility. You only have 4 unknowns that you can fix, in a sense, in this case. Okay, so what I would talk about, which was actually given as the main subject, the main topic of this talk, is to think about this thing in a little bit more differently, this resummation, a little bit. So let's start by asking the question, what is this expansion? What are these expansion coefficients? This chi b of m, this susceptibility, what are they? So this is, now it gets somewhat technical, but I will try to keep it accessible as much as possible. So what are they? The experts, I mean, people who do this all the time, they know this by heart, but what actually they are is this. So every pies are basically a combination of different diagrams. So what are these combinations? So there are combinations of some diagram where this and insertions like these blobs. So what these blobs represents is a baryon current. And this is pretty clear. The way to understand this is very clear. It's simple. So these chi's are derivative of the log of the partition function. But the partition function, the way mu enters the partition function is basically mu times the current, or mu times the number density, the integrated current, the integrals outside. So when you take the derivative with respect to mu, what you bring down, each derivative basically brings down the current. So these D's sub n, so each of them, each of these blobs are actually essentially a current correlation function. So in 4th order, you will have up to 4 current correlation function of 4 baryon currents. In the 1st order, you will only have 1. In the 2nd order, you will have 2, but it can come in 2 different varieties. I will get into that separately. So it can be either these two, in the 2 separate diagram, or it can come in a closed loop of 2 current correlation function. Now, if you stare at this a little bit, so what you can realize is this. So in the contribution to the pressure, so this diagram, this insertion, this diagram will be multiplied by mu b. These 2 diagrams, again, in the contributions to the pressure will be mu b squared by 2, and so on. So mu b squared by factorial 2, this is mu b cubed in the 3rd order, mu b cubed by factorial 3, and so on. So instead of looking at along this horizontal line for a moment, imagine I'm looking at this diagonal line. and just considering the diagrams which one current insertions and its powers like this along this red arrows. So you can immediately realize that if I'm looking at along this diagonal, then I can this thing up to all orders, I can simply exponentiate it. So that will give me an all orders resummation of these diagrams, all orders in mu. Similarly, things happens if you have just the two current correlation function. Again, if you look at the two current correlation functions in the second order, it also enters, the square of it enters in the fourth order. And what about the cross term between the two and the one current correlation function? You will see that enters in the third order, and the way it enters is exactly also the cross terms. You can, again, exponentiate this two current correlation function also. And it turns out you can also, the cross terms between the two current and one current can be exactly reproduced by just the multiplication of these two exponentials. So it is amazing. So you can just notice it. This is some sort of more started as empirical observation. So if you keep doing it, then you can realize this, and you can actually write the pressure or the pressure, the deviation of pressure from the zero mu v value, that's this delta pressure, as a log, an exponential version of the sum of this current correlation functions to the end. But obviously, what we need to calculate in Lattice is I don't have access to all orders correlation function. I only have access that I can calculate to any finite computing power. I have to truncate the sum to, but this time the sum is truncated not in powers of mu, but the sum is truncated in the number of the order of the correlation function. So what this resummation does in this case, this exponentiated version, is that it resums contributions of up to n point current correlation function, but to all orders in mu. So the truncation in this case is the how many current correlation function that you keep. But for if you have any computed anything up to less than n, then then its contribution to the pressure to all orders in mu that you can resum. So it's a different variety of resummation. This is not an expansion of mu. This is an expansion like a kind of more similar to the vortex expansion. So now what you can do is, if you can root it down, you can easily check, and again, you can see that if you expand this thing, expand this exponential in mu as well as this log and so on and so forth, what you get is exactly what you reproduce is the first, you reproduce the Taylor's expansion up to nth order. So if you have capital N number of correlation function, you will reproduce the Taylor's expansion mu to the capital N, plus it will also have all kinds of correlations of all orders N.
Swagato,
Yes.
I have a small question, quick question. So you're thinking of this expansion as an operator exponentiation as an operator exponentiation, right?
Yes, yes. That's the way I'm thinking, at least.
Okay, thanks.
I will try to give you a much more intuitive and just in the next bit. So what actually have we done? So what did we do here? I mean, this is just a very technical way. I mean, unless we have been dealing with like this or me, Surendu, for the most of our life, you wouldn't write down and see this. This is, I mean, this is just something happens because we know this. We have stared at it for so long. So what actually happened physically? What actually we did do? What just happened? So what we did is basically we wrote down an effective fermion action. So let me try to explain how to get some, at least it might not be very solid, but at least to have a feel of the physical intuition, how it feels. At least that's how I feel my intuition. So we are talking about a global charge. Baryon charge is a global charge. And I have a lattice, which is, in this case, I have antiperiodic boundary conditions because of the fermions, and that the extent is just the inverse of temperature. Now, since this is a global charge, I can take my chemical potential and put anywhere in the box. So I choose to put it at the boundary. So I just shift all the chemical potential dependence to the boundary. That can be done. So now, what is the mu then? Once I put it in the boundary, so this blob that I show is basically this d's, which is just a baryon current, which means in this case that your fermion is moving in one direction and the antifermion is moving in the opposite directions, and then the insertion is the gamma naught. So that's and once this fermion antifermion pair crosses the boundary, the fermion crosses along this way and the antifermion crosses along the other way. Then to cross this boundary of a named baryon, you need an energy, and that energy is exactly mu b. That's how you define mu b. The energy that you need to add a fermion or antifermion pair to your heat pipe, to your system. In this case, we have a periodic system, so adding this means it's just going across the boundary. So now I can do it various ways. So if I do this one time, so the energy, then this is d1, the energy becomes d1 times mu. Now, the second time, what I can do is I can think of two ways. So I can start from here, I can go along and cross the boundary 2 times. That is basically d2. If I go and wrap around 2 winding numbers, basically two times. So I will cross my boundary 2 times at the same time, connected wise. And that's the energy that you need is d2 times mu squared. Now, instead of doing that, I could have also done that. And so I could have chosen 2 separate fermion antifermion pair, each of them going along separately without connecting each other. So this one will be basically then d1 and then 2 times squared. And obviously you can also think about the permutations and all these factors. You can also, it's just a permutation of this. You can also explain this factorial. So the energy, the partition function in this case will be the sum of the energies. And what we basically have written down is an effective fermion action, but on a given gauge field. This, what I'm writing is on a given gauge field. So if you are given a background field, then you can write down the fermion action in terms of this winding numbers. So in the given gauge field background, I can write down a partition effective action, which is mu times this effective number density. But this effective number density itself is a function of mu b. And this effective number density is basically the sum of this winding numbers, which is basically the sum of the energies it takes to add fermion pairs in different combinations. So this is basically intuitively what has been done. This exponentiation means. So if you're asking for a formal proof, once you realize this and once you see this pattern, the formal proof is basically trivial. It's at least it turns out to be completely trivial. So you look at the partition function. The partition function again. So itself the partition function. You can write the average value. You can consider this determinant itself as an observable. So this partition at mu equals mu b at observable. So the average partition function at non-zero mu, you can itself write it down as the expectation value of the determinant at non-zero mu b, but this average is taken over the zero field ensemble. Now, there's a trivial identity that you can just go by diagonalizing in the diagonal basis that det m is exponential to the trace log m. So now instead of expanding the partition function, what I'm doing is I'm just writing a Taylor's expansion of this trace log m. I'm not expanding anything. I'm not expanding exponential and etc. Just it's trivial. I'm just expanding this trace log m. So what you get if you do this, then it's essentially that it is an approximation because you are truncating it to some orders in the correlation function. So that is an approximation to your actual partition function. So this resum partition function that you can write is simply like this. And this is an exact proof. It's a trivial but exact proof. So now this partition function contains now all orders in U. So it is not a polynomial in view anymore, so you can determine its zeros. So you can find or try to track its non-analyticities as a function of mu. And which also means the pressure that you get is basically log of this partition function. So when the partition function develops as zeros, then all thermodynamics breaks down. The pressure breaks down. So you can also find this also gives a self-consistent check to the reliability of your QCD thermodynamics of your results. So remember, this is not an expansion of the partition function. The partition function is defined once you sum over all the gauge fields. So I'm not expanding the partition function. I'm expanding the fermion action on a given gauge background. Now, if you try to expand the partition function, all the singularities and the periodicities, the singularities are of the partition function. It only arises once you make the gauge average. On a given gauge, there is given background, there is no singularity. The Youngly Age singularity, or say, for example, the Fermi-Dirac distribution arises when you sum over the fluctuations of the gauge fields. That's the fluctuations of the quark loops. They are distributed around according to the Fermi-Dirac distribution. So expanding the partition function, which is after integrating of the gauge fields, means it has to be limited by the singularities of the partition function. But in this case, I'm expanding on the given gauge field background and then averaging after that. So there is a possibility that I can actually bypass or go actually resum these singularities of the partition function and probably go beyond. That's just a hope. But this seems just absolutely too simple when you try to write this. So it looks trivial. So, but does it work? What can I do? I mean, to see. I can sort of obviously try and see. It is hard to prove and show this in the case of a real lattice calculation. That gets too complicated, but I can try to do it in a simple solvable model. So I choose one model which can be done, and without giving much details because that part is not terribly critical, or neither there are some interesting physics in it. So this is a mean field quark meson model, some model, which I can solve exactly in the mean field. So in this case, I can compute two variations. Say this is the baryon number density. So I can look at the baryon number density as in a standard Taylor expansion manner for different orders in expansion from 6 to even 14. Obviously, I cannot do this in a real calculation. That's why I chose to do it in a model just to see this. And this is the resummed version. You again calculate the same number, baryon number density, but this time in the resummed version of the expansion. And I do this in both cases as a function of mu. The way I show it is in terms of mu squared, but the positive axis means that I have purely real mu, and the negative axis shows I have purely imaginary. So I want to look at this in the full complex mu plane. So I'm just, for simplicity, I just chose the purely imaginary mu, that which is depicted along the negative mu squared axis, and the purely real mu, which is depicted along the positive mu squared axis. And the things are scaled such that with the periodicity, let's not get into there. And these lines are basically the Youngly Age that I can, this is a solvable quark, solvable model, so I can compute also exactly the Youngly Age singularities in this model. So as you can see, and there's black lines in both cases, which you wouldn't see on the right-hand side. The black lines are the exact results that I can compute here. So if I go and see how the Taylor's expansion behaves in this case, so this is the 6th order. I'm starting with the 6th order, which is already sort of putting the state of the art in real calculations. So this is 6th order, and then going up to 14th order, and compared with the real actual results, which is this black line. And as you can see, both along the imaginary mu and the real mu, as we expected, the Taylor's expansion actually breaks down at the Youngly Age. Now, when it comes to real, the resum version, again, here we start from n equals 4, which is perfectly doable. And then it's just from 4 to, we check up to 12. and compare it with the full results, basically, I mean, it is completely, to my surprise, that it works so good, even at the lowest order, like in our 4 expansion of, obviously, this is a model, and it does not even break down at the real singularity, it just goes forever. I mean, at least in this case. Of course, in this particular case, it breaks down at the periodicity of the partition function because it's a mean field artifact. Let's not, I mean, if you want, I can talk about it later. Okay. So, but it just follows the real result, but can it capture or at all capture the Young Age singularities? It turns out it does. So you can also compute the zeros of the partition function. I mean, this we are doing, this is infinite. We have already taken the infinite volume limit. So there are no zeros in this case. So these are purely cut. When you're doing a finite volume, there won't be any pure cut. So you will just only find order volume zeros. So in this case, you can compute the Young age itself from either by using this resummed version or by using the exact version. So if you use the resummed version of the partition function and compute the Young singularity, this is this green, yellow, and blue points are the Young age singularities coming from the resummed up to this orders in n. So, and compared with the full result, which is also again the black dots. So as I said, this is real mu, real mu, imaginary mu. If you can see, and it is done for different temperatures, and you start from there, it exactly, even at lower order, almost exactly reproduces the singularity. This resummed version, lowest order resummation, even reproduces the singularity. You come down in temperature, and at some point, it is shown by this in the real calculation, it pinches the real axis. That is actually your critical point, where you have a singularity again at the real axis, right on the real mu b. But it works pretty well up to pretty low temperature, and then what happens is it breaks down because your periodicity becomes closer to the Young age singularity. In this particular, that's a pathology of this model. So in this particular model, that happens.
Again, a quick question, Swagato.
Yes. Yes.
So this singularity, I missed it. It's a branch point, right?
It's a branch cut. Yes.
Okay.
It is. Okay. Let me go back. So in the scaling, it is a branch cut.
I understand. It's fine. It's fine. I mean, I wanted to verify that it's a branch point.
Yeah, and what we are trying to find is where it starts. That's basically what we are doing. Okay, so fine. Mean field quark meson, easy. I mean, it is probably anyone can do it, but is it at all realistic for any real lattice QCD calculation? So let's try it out. So this is a pretty realistic calculation. This is physical quark masses, pretty realistic lattice sizes, 8 times 32 cubed. So it's very large compared to any reweighting or anything that has been done. And this is super high statistics compared to any calculations. Also, most of the people, this is like 500,000 configurations and goes into there probably in various cases. So here again, in the left-hand side, I show the pressure. In the right-hand side, the baryon number density. Once again, as a function of mu, the positive mu squared axis is real mu. The negative mu squared axis is imaginary mu. This is sitting at a given temperature, 157 MeV, which is very close to the transition temperature at 0 MeV. So what do we see? So I will just discuss on one plot. Let's take the right-hand side. So the bands here, what is shown here, so this green one, the red one, and there's some blue one in behind it, are the bands that you will get for this quantity, in this case, the number density, from Taylor's expansion. So this is the second order Taylor's expansion. The blue one is the fourth order Taylor's expansion, and the red one is the sixth order Taylor's expansion. As you can see that from going from second to fourth, it is already a huge jump. the Taylor's expansion, the convergence of the Taylor's expansion, you see that from second to fourth, and then in sixth order, it just grows bigger. Convergence is slow compared to that with the resum version. So again, which are these open symbols in this case, second order, fourth order, sixth order, even up to eighth order in this case. And here again, you can see that in the resum version, the convergence is unlike from the second order to fourth order, this jump. In the resum version, it is very decent. And up to a certain point, this of mu b squared of say 2.5, it doesn't agree with Taylor's expansion. So it is at least gives a better convergence, but it does not mean it is a correct result. So maybe these bands are the correct results. So what is happening? What does it mean? And in the negative direction, it just breaks down again at mu squared of 2.5, but it just breaks down. It's nowhere close to the Taylor's expansion. So what is happening? So is this calculation at all reliable? So in this case, what we can also do is we are resumming, so we are writing a resummed version of the partition function. So which means I can also compute the average phase of the partition function, which gives me the real severity of the sign problem that to begin with sort of hinders my real calculation. So I can write a resummed phase factor, again up to nth order, up to taking it to up to n order correlation function. So this is the average phase of the partition function, this resummed phase that you can also compute. And again, this resummed phase as a function of mu b are shown in the open symbols for the resummed version for different orders, second, fourth, sixth, and eighth. You see perfect convergence. There's nothing that shows anything else. So and you compare it with the Taylor's expansion. So what happens if I try to compute this in the Taylor's expansion, basically, which will be an expansion of this phase here. So up to this, so look at this. So this is the second order. It goes down and dives to 0. Then you go to the fourth order, it just jumps in the opposite way. So if you are doing a real calculation, you would see that there is no severity of this sign problem and it goes to infinity. You can do probably anything. You go to the sixth order, it dives down the other way. So it's absolutely no sense of convergence unless you are really sitting at a very small values of it. On the other hand, it converges very well for the resum case. And not only that, what it tells is, say, around a value of mu b by t of say 1.5, this average phase factor is 0, which means from configuration to configuration, the fluctuations of the phase is huge so that it averages out to 0. And that is the seriousness of your sign problem. So the reason it deviates from the Taylor's expansion and this results is basically around this point, your average phase factor basically gets 0. This is the sign problem is really severe. So this 1.5 would be basically mu squared of 2.5, 2.25 or this range exactly here where it happens. Okay, so this goes to the average phase factor that what happens to it. You can make it more detailed into it. As I said, you can even compute the zeros of the resum partition function. So you compute the zeros of the resum partition function. So this is, in this case, the red ones are for the sixth order resum partition function, the blue one are the eighth order. So more or less, I mean, okay, so the one thing I must say that these zeros are done very crudely. This is not something, a state-of-the-art determination of the zeros of the partition function. These are very crude. It's just to have a qualitative feeling, but it does, it works. So if you see basically what happens, so you see that this at 3 at the purely imaginary axis is basically, this is probably the reminiscent of the periodicity here, and from going from 6th to 8th order, it more or less is stable. And what you see is there is no 0, the critical important thing that there is no 0 between the, say, a mu b of t, or at least we didn't find any 0 in the mu b of t of 1.5 around. And all the 0 starts from beyond. So just a fun stuff. if I just take these zeros and compare with the Youngly Age singularity, that estimate that I did for a very idealistic continuum case with all universal values and so on. So that would be here. So this is for the O4 universality, this is for the O2 universality, just because that's a lattice artifact. And this, I don't want to go to that technicality, it doesn't really matter. And obviously these are cuts and these are at finite volume. So you really need to do finite volume scaling and so on to see whether it has anything to do with this or something else. But at least what you can do, what this method can do, it gives you a cell cost consistent check when it breaks down. You can follow the zeros of the partition function, you can follow the average phase factor, and you can sum up to all of this in mu b, but an expansion in the number, the baryon current, the operators in this case. Okay, but what about the variant? That must be better. So that has pushed to many things and sort of even can go up to probably the periodicity and probably can cross it. That must be better. Maybe it is better, but let's talk about the philosophy and what we can do is we can generalize this whole resummation for multi-parameter resummation. So this is something that was not there in this paper. So we just updated it because it came late. So nothing in this whole talk happened really quite chronologically the way it was presented. It sort of just happened, and I'm just gelling it together as best as I can. So let's see, what's the idea? So here, let's see that I'm at exactly sitting at the chiral limit. In the TMUB plane, I'm sitting at the chiral limit. So this is green line is the phase boundary. So my expansion breaks down at the phase boundary. That's my Youngly Age. In this case, it's on the real axis, but it's still in Youngly Age. But I want to go to at certain values of mu, which is at this temperature, which is beyond the phase boundary, going a larger mu than the phase boundary. I cannot just do a simple expansion, it will break down here. But what I can do is I can think about doing, I can basically try to, so in this case, this is the broken phase, this is the symmetric phase on that side. What I can choose to do, I can choose a point where I'm staying in the symmetric phase. So if I stay in the symmetric phase, then in the same phase, then I can expand up to there at a different temperature. I can expand in mu, and then I come back in temperature. That is basically the idea of the variant, I think. So again, the only point being that I can, to what point in T prime I can expand. The T prime I can expand. In this case, there is no singularity in the pure real axis, but there is a singularity in the complex plane, which is shown in the negative mu squared side. So it will be hit by this boundary. So that's why this choice of a physically motivated path is important. So you have to choose somewhere where this mu b is, the temperature is such that you can go up to this value of mu b. Maybe you have to stay here and expand this from here in this case. But what you can do is in this case, the way you can generalize this, so you can again choose to look at this operator expansion by doing, in a sense, which is called a multi-parameter relating kind of a thing. So in this case, the difference of the configuration between the symmetric and the broken phase is too different. The configuration themselves are too different. So if you cannot push to starting from a symmetric phase, you cannot cross and go to the starting from the broken phase, you cannot go to the symmetric phase. So you can just, so that's called the overlap problem. The configuration, underlying configurations are too dissimilar. So you choose a configuration which is in the symmetric phase and go to first expand in mu, and then try to reweight these configurations in the symmetric phase now within two different temperatures. So that would be that I can write down and expand also this in the coupling in this case. So I can, this is an exact thing to do. So I can write down the ratios of this partition function T mu b with respect to some different T naught and 0. So that would be my gauge action plus the determinant of the fermion action and the overall average. Now, as before, I can expand this fermion action. I can do generalized expansion in M, U, and everything and whatnot. Forget it, it does not really matter, but I can really write it down. And now what I can do is, this is my generalized resummed version. Then I can do an expansion in both mu and delta beta. Forget delta M for now. So delta beta is the Bayer gauge coupling. These Bayer gauge couplings are related to the temperature. So T naught would be beta naught, and so on. Now, if I expand both jointly, both this exponential in mu b and also in delta beta, what would I get? So eventually what would I get are things which are sort of correlations of the gauge actions with this operator. So you can immediately realize and write down this is nothing but the temperature derivatives of this operator. You can actually exactly do this. So what this expansion in all parameters entails to the leading order, what you can immediately see is basically a joint expansion in temperature and chemical potential. So the generalization of this resummation that we introduced is basically a resummation of this new variant when it resums all powers in mu and all powers in T up to any endpoint correlation function. Okay, so I think I stop here. Probably right in time, or probably a little bit more. And let me try to summarize. So what did I do? At least just to summarize. What I said is that Young-Lee Age singularity limits the Taylor's expansion in chemical potential. This is an universal singularity, but the mapping from this universality class to the QCD is non-universal, but that also can be handled to some extent with lattice calculation. I proposed a resummation scheme of the Taylor's expansion that can capture this Young-Lee Age singularities and even go beyond. So this resummation scheme is up to all orders in mu. It resums the contributions of up to n point current correlation functions to all orders in the chemical potential. It also provides you a self-consistent check of the reliability of the results. It allows you to determine the singularities of the partition function. I demonstrated the efficacy of the scheme within a solvable model and showed that resummation actually accurately captures the Young-Lee Age singularity and gives accurate results even beyond that. I demonstrated that this method is not just a dream, it can be practically applied to any realistic lattice QCD calculation. I also provide a generalization of the scheme that can simultaneously resum in multi-parameters like temperature, chemical potential, and even in quark mass, which becomes the generalized resummed version of this newly introduced variant of the expansion. Thank you. So I hope that it was understandable to somewhat. It was a technical topic, but please go ahead. Any questions?
Yeah, thanks, Swagato. Let's thank Swagato for this colloquium. Maybe you can unmute your mic, or you can use the reaction window. I think we have time for questions. So I already see Surendu has raised his hand. Surendu, please go ahead.
Yeah. Hey, thanks, Swagato. That looks like a really impressive advance, but you didn't tell us about how difficult it is to compute the exponentiation numerically. It's order by order, right?
Yeah, at least for this calculations, we have tried with this volume that we use, the lattice sizes. It works actually, at least so far, it has not broken down for us because we ran into a large number where I couldn't compute the exponentiation. Before that, I hit the zeros of the partition function, at least in these realistic cases. Eventually, it might happen. if you go to very large volume.
Right, but okay. So my question really was that when you exponentiate the first order thing, and you compare it to the exponentiation of the second order thing, or then the number of then the amount of fermion Monte Carlo time that you need must be different, right?
Oh, you mean the gauge number of gauge fields that we use?
No. For each gauge field, yes, when you're evaluating the exponential, you still have to do that Monte Carlo, right?
Oh, you mean that's to compute the traces?
Yeah, right.
Of the operator.
Yeah.
Okay. So the traces of the operators were okay. So this is something which I did not go into because of this technicality. So what we did is the at least in this calculation, and actually I also don't know how to do it. I haven't done haven't evaluated the exponential in an unbiased manner. So it is so if we what we did is we checked whether given with a number of stochastic random vectors to evaluate these traces to see whether how it compares with the expanded version of it. But when we put the exponential, it is not an unbiased estimator. But we used like at least for the first order like 1,000 about stochastic estimators, and for all higher orders about I think 500 to 700. But I think what you are thinking of that whether I evaluate the exponential itself not unbiasedly.
Yeah, right. Yeah. Okay.
Yes, I did
Thanks
not do
for the
that.
clarification. Yeah.
Yeah,
I'm sorry.
I had this.
Yeah, please.
Yeah, I had the similar questions like the higher order. How do you control the error? The error will also increase dramatically, isn't it? Yeah. If you don't do unbiased for it, yeah.
The unbiased traces, or I mean, error in terms of gauge field configurations, you do whatever you do, right? But for higher orders,
not gauge field. I mean,
the estimators.
Yeah.
I don't know all I can do is all I can check is at least to some leading. I mean, you can compute your exponential, and you can also try to compute the expansions of this exponential to some point in unbiased order to the lead. To some orders you cannot obviously do for the whole thing, and at least what we checked is that works at least within our available computation. And also, at least it also works in terms of the results, the full results, as we showed, at least agrees with our unbiased calculations in the Taylor's expansion. That's all I can say. I don't have any better answer to this. Because it is not, at least I don't know how to do an unbiased exponential. Maybe some of you do. I mean, maybe I can think of something, but at least it wasn't there. But we did check that I mean, we were certainly aware of this issue. And so we did check the best that we could do. We changed the obviously different and tried with different number of random vectors to estimate it and check whether it is stable or not. That's all. What else can you do, right? So do you have any suggestions how to control it? Just to apart from empirically checking it.
No, I mean, you can probably put some different type of noise vectors and see how it's changing, and also like some dilution type.
Yeah, okay, but that is just itself to compute the traces.
Yeah,
right?
yeah.
That does not solve the problem of exponentiation, because the value of the traces does not change no matter how you compute. I mean, it should not if you use have sufficient sampling. I mean, obviously, I mean, that has been checked by when you compute the traces. We have checked by using Z2 or random vector or Gaussian and so on. Those are standard procedure that has been done long time ago. And we also tried dilutions for some reason. Some reason does not work for staggered that simply. I mean, I know to some extent why it doesn't work, but it's not that simple.
Surendu, do you have another question? Or?
Yeah, right. So I just wanted to change the topic. And I mean, Shagati, in this talk, all the figures that you show are at about 157 MeV of temperature, which is roughly where the phase transition takes place, at the crossover takes place. Now, if this thing works so well, then it would be interesting to check what happens at substantially lower temperature, let's say 120. You must have checked that.
No, we haven't. We don't have data to 120. I can tell you that we have generated tons of things at 125, but we haven't done it. And first of all, this is not done in a big hot QCD, so it will take time. We have the data. Someone has to do it, and someone probably will do it. But it is an interesting question. I mean, since we are okay. Can we finish the questions and then we can discuss? I mean, I have other things. I mean, if we can just simply want to discuss, I would be happy and I would love to.
Sure. I mean, we could wait until others have finished and then.
Others finished and then we can discuss, I guess.
Shagato, I missed one very basic thing. How was the mu introduced here? Was it linear or exponential?
So pretty much, I mean, it doesn't matter, and it is not any different from Taylor's expansion. It was introduced in this particular case for up to fourth order in exponential, and then up to higher orders in linear. What we did is basically we just took because these are part of your Taylor's expansion calculation, so we just used those. So whatever we use for normal Taylor's expansion, it is exactly the same. Nothing changed. We actually, it's a question that we worried about too. We can again, whether you have divergences in that case, but actually once you do the whole thing, it turns out there is none.
Oh, thank you.